In Unit 3, we're going to be learning about basic atomic structure. So last week, you took a look at the timeline of an atom, looking from where we started up through almost present day. So we're going to start with the really early atomic theory. Some of this will be a recap and some will be something new. So the first person to come up with an idea of an atom was Democritus. And he hypothesized that everything was made up of either empty space or tiny indivisible particles that meant atomos. So essentially, you could take any substance and you could keep cutting it in half until you got to a substance that was so small you couldn't cut it in half anymore, and that would be an atom. So if I were to take a piece of paper and rip it up a whole bunch until I got to a piece I couldn't rip anymore, that would be a paper atom. And each substance was made up of its own type of atoms. Now, people ignored him for almost 2,000 years because at the time there were prominent philosophers, Aristotle and Plato, who thought that everything was made up of some combination of earth, air, fire, and water. Now, we're going to skip from atoms just for a quick second. We're going to look at the French in the Age of Enlightenment. So there was a famous chemist named Antoine Lavoisier. Now, he was the first person who did experiments in a quantitative way. So remember, quantitative means numbers. So what he did was he would complete chemical reactions in what he called a closed system. So just think about it. Closed system essentially means nothing's getting in and nothing is getting out. And what he realized is when he put these chemicals together in the closed system, and we saw a sign of a chemical change, whether a gas was being released or a new solid was formed. But what he noticed was there was no change in mass during these reactions. And that ultimately led to his discovery and him publishing what we now call the law of conservation of mass. Now, the law of conservation of mass essentially just tells us the mass before a reaction is going to equal the mass after. Lavoisier was also credited with a few other things. He put together the first extensive list of elements. He helped construct the metric system. He helped reform chemical nomenclature, which is essentially how we name chemicals. And he was sentenced to death by guillotine by the revolutionaries. Now, Joseph Proust was another chemist at this time. In 1794, he published what is known as the law of definite proportions. Now, that law tells us that all compounds have the same ratio of elements by mass. So every time copper and sulfur come together, there will be 6.646 grams of copper and 3.354 grams of sulfur for every 10 grams of copper 2 sulfide, or CuS. Now you can see that here. So even if I wanted 10 times that amount, if I wanted 100 grams of copper sulfide, I would need 10 times the amount of copper and 10 times the amount of sulfur. John Dalton was an English school teacher, and he came up with the first testable hypothesis concerning the existence of atoms. So, rewinding back to Democritus came up with our first ancient theory of an atom. Now, he was ignored for 2,000 years until John Dalton came along and said, wait a minute, no, this whole thing called atoms, this makes sense. So he was able to confirm and expand upon the ideas of Democritus, Lavoisier, and Proust. He gave us quite a few really important pieces of information through his research. So he was able to tell us that everything is made up of atoms, and all atoms of a particular element are identical. So all carbon atoms are like all other carbon atoms. All hydrogen atoms are like all other hydrogen atoms. But he was also able to tell us that different elements are different because they're made of different atoms. So carbon atoms are different from hydrogen atoms, which are different than helium atoms, which are different from argon atoms, etc. And he also restated our law of conservation of mass to tell us that chemical reactions are just rearrangements of atoms. So there's no loss of mass because the chemicals or the elements are just changing places. He also restated our law of definite proportions to say that atoms combine in whole number ratios. And he was also able to prove the law of multiple proportions, saying that atoms can combine in several different whole number ratios. So the example that you can see here, we can have nitrogen and oxygen combining in a 1-to-1 ratio, or you can see nitrogen combining with 2 oxygens to make nitrogen dioxide or NO2. So not only does it combine in a 1-to-2 ratio, but it also combines in a 1-to-1. So Gay-Lussac, we're going to learn more about him towards the end of the semester, but he was a French chemist and a physicist, and he took gases at constant temperature and pressure and conducted experiments with him. And what he was able to realize is we're not only just combining atoms in definite ratios, but we can also combine identical volumes of gases in small whole number ratios. So rather than saying 2 hydrogen atoms plus 1 oxygen atom gives me 1 water molecule, instead he would say 2 volumes of hydrogen plus 1 volume of oxygen is going to give us 1 volume of water. This became known as our law of combining volumes. Now, the Italian physicist Amedeo Avogadro, he was able to then explain Gay-Lussac's law in terms of a new atomic theory. Now, his ideas were not accepted for quite some time. It was actually after he had passed away that his theories became accepted. So what he was able to figure out was equal volumes of gases that were held at the same conditions of temperature and pressure have the same number of gas particles. And he also told us that volume is directly proportional to the number of gas particles. Now that makes sense to us because we can see that if we have more particles, we're going to have more volume. We're going to be taking up more space with the more particles that we have. Now, that constant temperature and pressure is what we know as STP, standard temperature and pressure. That would be 1 atmosphere and 0 degrees Celsius. Now, at that standard temperature and pressure conditions, 1 mole of any gas is 22.4 liters. Now, you're going to watch another quick video on the mole, but mole is essentially our way that we say a dozen is 12. A mole is 6.022 times 10 to the 23rd atoms. And depending on the element, it's going to have a different mass. But at standard temperature and pressure, that mole of atoms takes up 22.4 liters of space. Now, the most confusing part of all of this is 2 plus 1 no longer equals 3. So in chemistry, we look at things and it might be 2 atoms plus 1 atom give me 1 molecule. Or 2 liters of hydrogen gas plus 1 liter of oxygen gas is only going to give me 1 liter of water. So we have to now lose that idea that 1 plus 1 is 2 and accept that it may be something different. Now, the law of conservation of mass is still going to tell me that we're going to have equal number of atoms on my reactant side as we do on our product side. So we can see we have 2 hydrogen atoms plus 1 oxygen atom, so that gives me 3. It's going to be 1 water molecule, but the 3 atoms are still there. They have just been rearranged.